Hi guys, welcome to enginerdmath channel. We're live. Our topic for today is all about finding Laplace transform using its definition. Okay? So, we will try to find the Laplace transform of function, let's say function of time, t, or usually we use t here in function wherein we try to find the Laplace transform of f of t, and it will become function of s because we have an integral transform definition for Laplace transform. So we will derive several standard formula for Laplace transform here, and later on those derived formula will be used to find easily the Laplace transform of any function of t. Okay? So, what's the definition of Laplace transform? Or what is the formula in finding Laplace transform? So, definition of Laplace transform. So, we have Laplace transform of, so this is the symbol for Laplace transform, this curly L or cursive capital letter for L. And if you want to find the Laplace of Laplace transform of any function, let's say f of t, okay, it is equal to the integral of e to the negative st times that function f of t dt from 0 to infinity. So here we have improper integral, okay? Integral of e to the negative st f of t dt from 0 to infinity because one of the limit is infinity. So this is a unilateral definition for Laplace transform because we have a lower limit of 0 and an upper limit of infinity, positive infinity actually. So we will derive all the standard formula for Laplace transform using this formula. So when we get the Laplace transform of this f of t, it will become function of s. Let's say capital F of s, okay? So you convert the function of t into function of s when you get the Laplace transform of f of t. Okay? So to illustrate how to use this formula to find the Laplace transform of function f of t, let's solve some examples. So find the Laplace transform of the following. First one, we have f of t is equal to 1. Okay. So we need to find the Laplace transform of f of t, which is 1. So we need to apply the formula here. So it is equal to the integral of e to the negative st times f of t, which is 1. So we multiply e to the negative st by 1 dt, then limit from 0 to infinity. So since it's just 1, it is just equal to integral of e to the negative st dt, right? From 0 to infinity. So we will apply what we've learned from your integral calculus, how to integrate this one e to the negative st. We know that the formula for the integral of e to the at dt is equal to 1 over a e to the at plus c. So here, the a is equal to negative s because s here is a constant because the integration is with respect to t. So our independent variable is t and we can consider s as constant. So applying this formula for the integral of e to the negative st, it's simply equal to 1 over a, which is in this case negative s, then copy the same function e to the negative st. And since we have a definite integral, we have a lower and upper limit from 0 to infinity, we need to evaluate this indefinite integral from 0 to infinity. Applying the definition or the process in evaluating definite integral. Actually, the formal way of evaluating an improper integral is to use limit. So this is actually evaluated using limit, which is limit of negative 1 over s e to the negative st from 0 to b as b approaches positive infinity. Okay, so we will evaluate first this the indefinite integral from the lower and upper limit. So let's substitute first b to every t. We will have the limit of, okay, negative 1 over s e to the negative st, replace t with b. Then minus, substitute this time the lower limit 0 in t. So we have negative minus negative 1 over s e to the negative s times 0. And then as b approaches infinity. So if we try to simplify, limit of negative 1 over s e to the negative sb, this will become negative of negative 1 over s, so it will be positive 1 over s. Then e to the negative s times 0, it's e to the 0, right? But e to the 0 is just 1. So we need to multiply 1 over s times 1, which is still 1 over s. Okay. Then, as p approaches infinity. So, we need to evaluate this limit. Okay? So, the second term, 1 over s, is independent of b because there's no variable b here. It's just in terms of s. So, its limit, as b approaches infinity, it's still the same, 1 over s. The problem is the first term. How do you find the limit of negative 1 over s e to the negative sb as b approaches infinity? So consider cases of powers of e. If you have e raised to positive infinity, what will be the value? Let's say you substitute big value here instead of using positive infinity. Let's say e raised to 9999 and so on. Okay, if you use your calculator, you will notice that it will become large, right? Let's just input, let's say 39. Okay, it's already error, meaning it's too large already. Let's just use e raised to 99. Okay, notice that it becomes a large number. It approaches positive infinity. So when you raise e to positive infinity or any large number, it approaches infinity as well. How about if you raise e to negative infinity? Meaning, let's say, e raised to negative 999 and so on. Let's try. So, e raised to, let's say, only negative 99. Okay, this time, 1.01 times 10 to the negative 43, meaning it becomes smaller and smaller, right? Or it approaches 0. So when you raise e to the negative infinity, it approaches 0. So we can apply restriction in S so that this term will converge, meaning approach 0 as b approaches infinity. Because if this term approaches infinity, there's no finite value, this term will diverge. Therefore, the whole expression will also diverge because this one is infinity plus any constant term or any other value, it will still become infinity, right? So our goal is for this term to approach 0 so that this limit will converge, okay? So if it will happen if you set s greater than 0, right? If s is positive. Because let's say if you assign s equal to 1, which is greater than 0, you will have negative 1 over s e to the negative 1b or simply negative b, right? But since b is approaching infinity, you can substitute, let's say, an infinity here, a large number, let's say 9999. notice it will be e raised to negative infinity due to the initial negative sign here, right? Okay. So therefore, it will be equal to 0 based on this formula. Okay. Therefore, if we assign s is greater than 0, the limit of this term as b approaches infinity will be 0. It will converge to 0. So if you set s less than 0, it will not converge because let's say you have s is negative 1. So it will be negative 1 over s e to the negative of s. The value that we assign is negative 1. Then b. So negative times negative, it will be positive b, right? And since that b is approaching infinity, if you substitute infinity here in place of b, it will be e raised to positive infinity, which will become positive infinity. It will not converge. It will diverge to positive infinity. There will be no finite value. So we will avoid this value for s less than 0 because it will make this expression, its limit as b approaches infinity, diverge. So what we will just accept is s is greater than 0. So therefore, applying that restriction for s, we will have the value of the limit. Okay, if s is greater than 0, so the limit of this expression will be 0. We will have 0 plus, so like what I've said, it's just a constant with respect to b. It's independent of b. Its limit as b approaches infinity, it's still 1 over s. So therefore, the final value of the limit, so the Laplace transform of 1 is equal to the final value of the limit, which is 1 over s, for s greater than 0. Okay, so this is one standard formula for Laplace transform. So Laplace transform of 1 is equal to 1 over s. Okay? Next, what if f of t is equal to t raised to n? Okay, so we apply again the formula for the definition of Laplace transform. We need to find the Laplace transform of f of t, which is t raised to n. So it's equal to the integral of e raised to the negative st times f of t, which is t to the n, dt from 0 to infinity. Okay, so we have a product of e to the negative st and t to the n. So how do we evaluate this type of integral? We can use integration by parts, right? So using integration by parts, or IBP for short. So the formula for integration by parts is integral of u dv is equal to uv minus integral of v du. Okay? So if we let u be equal to t to the n, because what we have here is exponential function and algebraic. Applying lie 8. So since a comes first before e, we prioritize a, or the algebraic function, to be our u, which is in this case t to the n, right? So we let u be equal t to the n, and automatically the remaining term, e to the negative st dt, will be our dv. So dv is e to the negative st dt. So we differentiate both sides. Derivative of u du, derivative of t to the n, that's nt raised to n minus 1 dt, applying power rule, right? For dv, we integrate both sides. So integral of dv, that's v. Integral of e to the negative st, so we already have obtained the integral of e to the negative st on the previous problem, right? It's just negative 1 over s e to the negative st. So we have integral of e to the negative st dt is negative 1 over s e to the negative st. Now, applying this formula for integration by parts, we have the integral of the original problem, e to the negative st t to the n dt from 0 to infinity, equal to uv. U is t to the n. V is negative 1 over s e to the negative st minus the integral of v, which is negative 1 over s e to the negative st du, which is n t to the n minus 1 dt. Okay? But we must also put limit here since we're evaluating definite integral, actually improper integral. So for this term, we must put from 0 to infinity, and also in this integral part, let's put lower limit of 0 and upper limit of positive infinity. So just rewriting this term in a more suited form, or actually you can leave it as this, but it's better if you write first the coefficient negative 1 over s, then followed by e to the negative st t to the n, then evaluated from 0 to infinity, then minus for this integral part. So we can put the constant inside the integral in front, which is the constant term is negative 1 over s times n, because the independent variable is t, because we're integrating with respect to t. So negative 1 over s times n, or negative n over s, is considered constant. So since it's just constant, you can put it in front of the integral. So you need to multiply negative times negative n over s, so that will become positive n over s, right? Then integral of, so the remaining terms inside the integral will be e to the negative stn t to the n minus 1 dt from 0 to infinity. Okay, for this first term, we can apply the steps in evaluating definite integral. So we substitute first infinity, the upper limit, to every t, then minus, we substitute 0 to every t. We will have negative 1 over s e to the negative st, replaced with infinity, t to the t also will be replaced with infinity raised to n, then minus, okay, negative 1 over s e to the negative st, replace this time with the lower limit 0, t to the n. So replace also t with 0, raised to the n power. So let's analyze this first. So we will have negative 1 over s e to the negative s times infinity to the n minus, so this will become positive already, right? Because negative times negative is positive. 1 over s e to the negative s times 0 is 0. Actually, it will be 0 because there is a factor of 0 raised to the n. So no need to simplify this. It will be equal to 0 due to the 0 to the n factor, right? So how do we evaluate this limit when we have infinity? Again, just like on the previous problem, we involve e to the negative s times infinity. So if we assign a restriction on s, if s is greater than 0 again, this will approach 0, right? Because it will be e to the negative infinity. So therefore, this is just equal to 0, right? If we restrict s to be greater than 0. Then the next thing that we will simplify is this one. So this one is already 0, right? But we need to have this integral, n over s, integral of e to the negative st, t to the n minus 1 dt from 0 to infinity. So we don't actually need to simplify this because this turns out to be another integral. So we can eliminate this 0 and equate this to the left side, which is the integral of e to the negative st t to the n dt from 0 to infinity. But this is also the Laplace transform of t to the n, right? Which is equal to n over s integral of e to the negative st t to the n minus 1 dt from 0 to infinity. So this will be the formula for the Laplace transform of t to the n if we just use the definition, okay, of Laplace transform. But let's have a more precise formula. What if we want a formula that doesn't have an integral in its form, right? So if we try to let's analyze further. If we try to get the Laplace transform of t to the n minus 1, okay? And this is the formula for Laplace transform of t to the n. What can we do? So this time, if we assign n to be greater than 1, okay, because we're starting with the power of t now with t to the n minus 1. So applying this relationship, since our n originally here is since t to the Laplace transform of t to the n, the original expression that we want to find the Laplace transform is equivalent to this one. If we change the power of t to n minus 1, also all the n here will be affected. We will replace this n with n minus 1. Therefore, the Laplace transform of t to the n minus 1 will be, so replace all the n with n minus 1 since we're now finding the Laplace transform of t to the n minus 1. So it will become n minus 1 over s integral of e to the negative st t raised to this n, replace it with n minus 1 minus 1 dt from 0 to infinity, or it's equal to n minus 1 over s integral of e to the negative st t raised to n minus 2 dt from 0 to infinity. Okay. So, let's name this as equation 1. Okay, equation 1. And this is equation 2. So, how do we relate equation 1 and equation 2? We can actually substitute. So, this is n over s, right? We can actually substitute the value of the Laplace transform of t to the n minus 1 here, which is this one. This turns out to be n minus 1 over s. If you apply the definition of Laplace transform, you're trying to get the Laplace transform of t raised to n minus 2 here, right? By the way, this one for this equation 1, if you also relate the definition of Laplace transform in equation 1, you're also trying to find here the Laplace transform of t to the n minus 1. Okay. Sorry. Laplace transform of t to the n is equal to n over s times the Laplace transform of t to the n minus 1. Okay, but from equation 2, Laplace transform of t to the n minus 1 is equivalent to this one. Let's name this as 1 and 2. So if we substitute the value of Laplace transform of t to the n minus 1 from 2 in 1, we can have Laplace transform of t to the n equal to n over s times Laplace transform of t to the n minus 1, which is this one. We will have n minus 1 over s times Laplace transform of t to the n minus 2. Or this will become n times n minus 1 over s squared, Laplace transform of t to the n minus 2. Okay. Applying another iteration, let's say you get the Laplace transform of t to the n minus 1, you can still apply this formula, right? Or the original formula. So doing the iteration until we reach t raised to 0, you'll end up getting, so I won't show it anymore, the iteration, but there will be a pattern which if we continue the iteration, the Laplace transform of t to the n, you will see that it's equal to n times n minus 1 times n minus 2 dot 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 until 2 times 1 over s to the n. Then the last Laplace transform that we will have is t to the 0, right? But t to the 0 is equal to 1. Okay? Notice that this expression is equal to n factorial. The definition of factorial, right? Over s to the n times, so we know from example number 1 that the Laplace transform of 1 is, again, is equal to 1 over s. So if we substitute that value of Laplace transform of 1 here, it will be 1 over s. So you can still multiply the denominators, s to the n times this one is s to the first, visible exponent of 1, right? So n factorial times 1, n factorial, over s raised to, when we're multiplying same base, so copy the same base s and add the exponent, n plus 1. So we have s raised to n plus 1. This is for s greater than 0. Therefore, the derived formula for the Laplace transform of t to the n is n factorial over s raised to n plus 1, provided that s is greater than 0. By the way, I forgot to mention that n here, okay, n here should only be whole numbers. Okay, n whole numbers. Okay, so meaning n can take values of 0, 1, 2, 3, and so on. It can't have negative values or negative integers. Only positive numbers and 0. So there is a more generalized formula for the Laplace transform of t to the n if n is any number greater than negative 1 or any real number, I mean greater than negative 1, meaning it doesn't have necessarily be whole numbers only, it can be fraction decimal. So that's with the use of gamma function. So later, if we were able to solve that problem, we will find the Laplace transform of t raised to alpha, where alpha is not just a whole number but any real number greater than negative 1. But for now, so this is the answer. Okay, the Laplace transform of t to the n is, okay, memorize the second formula. Later in our future videos for this series of live stream for Laplace transform, we will just use the standard formula. We won't need to apply the integral formula to find the Laplace transform of t to the n. Okay? So the second standard formula, Laplace transform of t to the n, is n factorial over s raised to n plus 1, provided that s is greater than 0 and n here is whole number. Okay. Next, what if f of t is e to the at, where a is any constant real number? Okay. So, we will apply the definition again to find the Laplace transform of f of t, which is e to the at. So, integral of e to the negative st times f of t, which is now e to the at dt from 0 to infinity. So notice we have the same base e. We can just copy the same base e and add the exponents negative st plus at dt from 0 to infinity. We can actually factor the t here. Okay? Factoring out the t, or we can also factor out the negative. So we will have negative of quantity s minus a t dt. So I just factored out negative st plus at. It turns out to be negative quantity s minus at, because if you redistribute this negative and the t, you will have negative st, the negative of negative a, positive a, times t, positive at. Okay? Then, integral from 0 to infinity. So how do we evaluate this integral? Notice that this negative quantity s minus a is just a constant with respect to t, right? Because the independent variable here is t. So we can consider this negative quantity s minus a as constant. So applying the formula in problem number 1 for the integral of e to the negative s minus at, it's just equal to 1 over the coefficient. There will be this negative quantity s minus a, then times e to the negative s minus at. So since it's a definite integral, we need to evaluate this from 0 to infinity. Okay. So applying the process in evaluating definite integral, we substitute first the upper limit to every t. So we will have negative 1 over s minus a e to the negative s minus a infinity. By the way, we will apply the shorthand method already. We're now applying the shorthand method already in evaluating the limits, in evaluating indefinite integral with that are actually improper integrals. We don't use the limit notation anymore. So instead of using limit of whatever is the indefinite integral from 0 to b as b approaches infinity, this one is the notation that we use in the first problem, right? We use the notion of limit. But as a shortcut, from now on, I won't use this anymore. We will just use the notation, whatever the indefinite integral we have, we directly evaluate from 0 to infinity, meaning we can just substitute this infinity in place of the independent variable t, meaning that t is already approaching positive infinity. Okay? So going back here, after we substitute the upper limit infinity to t, next we subtract, then substitute the 0, the lower limit in every t here in the indefinite integral. We will have negative of 1 over s minus a e to the negative s minus a times 0. Okay. So, since we have infinity again here, it's under the exponent of e. We can assign restriction again for s for this term to the, converge. Okay? So how can we make this term converge given that its exponent is negative, the exponent of its negative quantity s minus a times infinity? So if we assign s to be greater than a, this will be approaching 0, right? This whole term. Okay? Let's say um you have negative s minus 1. For a, let's assign a equal to 1. Then you have this infinity here. So if you set s greater than the chosen value of a, which is 1, let's say you choose 2. Okay? Say s is 2. We have, so this is e raised to negative s minus 1 to infinity. So e raised to negative, substitute 2, 2 minus 1 times infinity, this turns out to be negative of 2 minus 1, which is 1, times infinity, or simply negative infinity. This is what we want, right? The e should be raised to negative infinity so that it will approach 0. So therefore, our assumption is correct that if we assign s to be greater than a, this expression or term will approach 0. Otherwise, if you assign s is less than a, let's say s is, since our chosen a here is 1, let's assign s to be less than 1, let's say let's say 0, okay? 0 because 0 is less than 1. If you try to plug in s is 0, we have e to the negative, so s minus 1, 0 minus 1 times infinity, e to the 0 minus 1 is negative 1, but there's still a negative here. Negative of negative 1 is positive 1 times infinity, or simply positive infinity. So if you raise e to positive infinity, it will approach infinity, right? It will not converge, it will diverge because there will be no finite value. It's approaching positive infinity. So therefore, we must not allow s to be less than a because the limit will diverge. But instead, we should use s greater than a for this limit to converge to 0. So applying that restriction for s to be greater than a, therefore, this value will be, so let's copy, the value of this limit will be 0 for the first term. Okay. If s is greater than 0 now, for this one, okay, this will have a finite value since we don't have infinity. What we substitute in t is 0. So we just simplify this. So negative of negative 1 over s minus a, it will be positive 1 over s minus a. Then e raised to negative s minus a times 0, it's just 0. But e to the 0 is 1, right? So therefore, we just have 1 over s minus a times 1. Or simply, 0 plus 1 over s minus a times 1 is just 1 over s minus a. And this will be true if s is greater than a. So therefore, the Laplace transform of the original problem that we had is to find the Laplace transform of e to the at, right? So the Laplace transform of e to the at is simply 1 over s minus a provided that s is greater than a. So this is another standard Laplace transform formula that you must memorize. Okay. So far we have derived the three Laplace transform formula. Okay, Laplace transform of 1 is just equal to 1 over s. Laplace transform of t to the n is n factorial over s to the n plus 1, where n is a whole number. And Laplace transform of e to the at is 1 over s minus a. Okay, next. Number 4. What if we have f of t is equal to sine? This time, trigonometric function. A again here is any real number constant. So let's apply the definition again. Laplace transform of f of t, which is sine 80, is equal to the integral of e to the negative st times f of t, which is sine 80 dt from 0 to infinity. Okay, how do we evaluate this integral if we got exponential and trigonometric? So we have a product of two functions. So obviously we can apply IBP again. So using IBP or integration by parts. So using Lie 8, what functions do we have? We have exponential. E to the negative st is an exponential function, right? Sine 80 is t, trigonometric. So since on the acronym Lie 8, t comes before e, we prioritize RU to be the t, which is the trigonometric function sine 80. Then automatically, the term that is not used, e to the negative sc dt, will be our dv. Okay. So we differentiate this, both sides, derivative of u du, derivative of sine 80. So that's positive cosine 80, but by chain rule, we need to multiply by the derivative of 80, which is a. So let's put a in front of cosine, then put dt. Then for the dv, we integrate both sides. Integral of dv is v. Integral of e to the negative s dt again, that's equal to negative 1 over s e to the negative st. So applying integration by parts formula, we have integral of e to the negative st sine 80 dt. Let's remove first the limits. So let's evaluate the indefinite integral. Then after we have obtained the final indefinite integral, let's just put the lower and upper limit. Okay? So integral now of this e to the negative s sine 80 dt using integration by parts formula. So that's integral of u dv is equal to uv minus integral of v du. So our u is sine 80. Our v is negative 1 over s e to the negative st. Then minus the integral of v, which is again negative 1 over s e to the negative st du, which is a cosine 80 dt. Okay? So, I will just put it here to fit on the page. So, we substitute du now, which is this one, a cosine 80 dt. So, just for writing the first term, we have, let's write the constant negative 1 over s first, followed by e to the negative st, then sine 80. For this integral, we can put the constant in front first. And what will be the constant here? So we're integrating with respect to t. So those variables that are not t are considered constant, which are negative 1 over s and a. So negative 1 over s times a, or negative a over s, is just a constant. We put it in front of the integral. We multiply by negative. So negative of negative a over s, that will be positive a over s. Integral of e to the negative st cosine 80 dt. Okay? But notice that we still have another integral of e times a trigonometric function, this time cosine. So this can be evaluated again using another integration by parts. Okay? So for the integral of e to the negative st cosine 80 dt, use IBP again. So if we assign our, let's say, u bar to differentiate it from the original variable u. So from lie 8, again, trigonometric comes first before the exponential. We prioritize cosine 80 to be our u bar. And automatically, dv bar will be the expression that are left, e to the negative st dt. So differentiating u bar, that's du bar. Differentiating cosine 80, that's negative sine 80, right? But applying chain rule, we still need to multiply by the derivative of 80, which is a. So let's put the coefficient in front. We have negative a sine 80 dt. Then for dv bar, we integrate both sides. So integral of dv bar, that's v bar. Then integral of e to the negative st dt again, it's negative 1 over s e to the negative st. So therefore, integral of e to the negative st cosine 80 dt, applying integration by parts formula, integral of u bar dv bar is u bar v bar minus integral of v bar du bar. So substituting the values, u bar is cosine 80 V bar is negative 1 over s e to the negative st, then minus the integral of V bar, which is negative 1 over s e to the negative st, then du bar is this one, negative a sine 80 dt. So rewriting this as negative 1 over s e to the negative st cosine 80. Then again, we put the constant in front of the integral. So the constant term here is negative 1 over s times negative a. So that's positive a over s. You put it in front of the integral. There's a negative here. So you multiply negative times positive a over s. That will be negative a over s. Then integral, what are left inside the integral are e to the negative st sine 80 dt. So this is the integral of e to the negative st cosine 80 dt, right? Okay. So therefore, this value of integral, these two terms, okay, can be substituted here. Remember, what we're trying to find is the integral of this one. Okay? So we're trying to find the integral of e to the negative st sine 80 dt, which is equal, let's copy this to this expression. Okay? So we already got the value of this integral, which is this one. We can substitute. So it is equal to negative 1 over s e to the negative st sine 80 plus a over s times the value of this integral is this one. Okay, let's just copy. Okay, we multiply by 1 over a over s. Okay, so distributing this a over s first. So copy the first term, negative 1 over s e to the negative st sine 80. So we need to add this a over s times this expression, distribute the a over s. So a over s times negative 1 over s, that will be negative a over s squared, right? Because s times s is s squared. Then copy e to the negative st cosine 80. Then also a over s multiply with this term, negative a over s, that will be minus a times a squared, over s times s squared, integral of e to the negative st sine 80 dt. And we equate it to the left side, which is the original problem, integral of e to the negative st sine 80 dt. So what do you notice? We have the same integral on the left and right side. So we can actually combine them. I will transpose this negative a squared over s squared integral of e to the negative s sine 80 dt to the left side, so that I can combine with this integral. So doing that, we will have integral of e to the negative st sine 80 dt. So from negative on the right side, you transpose to the left side, it will become positive a squared over s squared, integral of e to the negative st sine 80 dt, which is equal to these two terms on the right side. So let's just copy. Okay. Now, we can combine these two integrals. They are similar terms, right? So the first integral has an invisible coefficient of 1. We can add their coefficients, 1 plus a squared over s squared. Then quantity, this original integral e to the negative st sine 80 dt, which is again equal to these two terms on the right side. Let's just factor out common monomial factor here, which is the negative sign, and then e to the negative st. For the over s and s squared, let's just factor out the s squared. Okay. So if this is the common monomial factor that we have, what will be the remaining term here? So you factor out negative e to the negative st over s squared. We will have sine 80 times s, right? Because you factor out over s squared, you just have s over s here. Therefore, you must have s here in the sine 80 because s over s squared is 1 over s. Okay? Here, you factor out the negative e to the negative st over s squared. What is left? So, positive a, then cosine 80. Okay? Now, let's combine 1 plus a squared over s squared. So, this is equal to s squared plus a squared over s squared, right? Then, integral of e to the negative st sine 80 dt. So, equal to, again, let's copy the expression on the right side, this one. Okay. So, but what we actually want to find is not this expression. Okay, but just this integral of e to the negative st sine 80 dt. Therefore, we get rid of its coefficient s squared plus a squared over s squared. How? We just multiply both sides by the reciprocal of this. The reciprocal of s squared plus a squared over s squared is s squared over s squared plus a squared, right? So if we multiply this by s squared over s squared plus a squared, you can cancel s squared and s squared plus a squared. Therefore, you are left with the integral of e to the negative st sine 80 dt. Okay? How about if you multiply this by s squared over s squared plus a squared, the right side? Okay, if we multiply this by s squared over s squared plus a squared, you will cancel out the s squared. Okay, so you will have negative e to the negative st over this s squared plus a squared, then times the quantity s sine 80 plus a cosine 80. So this is the indefinite integral. But originally, we should have the lower and upper limit of 0 and positive infinity, right? So therefore, we must evaluate this indefinite integral from 0 to infinity as well. So substituting first the upper limit to every t, we will have negative of e to the negative st, replace it with infinity, over s squared plus a squared, then times s sine 80, replace with infinity also, plus a cosine 80, again, replace with infinity. Then next, minus this expression evaluated at 0, the lower limit. So negative e to the negative s, substitute this time t 0 with 0, over s squared plus a squared, then s times sine a, again t replace with 0, plus a cosine 80, replace again with 0. So the only problematic term here is the term with infinity, right? So just like on the previous problem, let's apply restriction on s for this term to converge, the power of e raised to negative s times infinity. So it's just the same on previous problem, number 1, right? If we just assign s to be greater than 0, therefore, this will approach 0. Actually, all this term will be 0. Therefore, we will have 0. Then, for this second term, negative of negative, it will become positive. E raised to, so negative s times 0, it's just 0, or 1. So, therefore, we just have 1 here on the numerator over s squared plus a squared. then times s. Sine a times 0 is just the same as sine 0. But sine 0 is just 0, right? So this is just equal to 0 plus a. Cosine a times 0, it's just cosine 0. But cosine 0 is 1. So we have a times 1 here. So simplifying, this will be 0. This will be just a. So 0 plus 1 over s squared plus a squared times a is just a over s squared plus a squared, right? So therefore, this is the Laplace transform. Laplace transform of sine 80 equal to a over s squared plus a squared provided that s is greater than 0. So another standard Laplace transform formula. Okay, so you must memorize this one. Okay, next. Problem number 5. Okay, for problem number 5, so if we have sine 80, we should also have cosine. Cosine 80. So let's derive the Laplace transform for cosine 80. Again, a here is real number constant. So applying the definition of Laplace transform of cosine 80 is equal to the integral of e to the negative st times f of t, which is cosine 80 dt, from 0 to infinity. Okay, so let's just use the results that we obtained from the previous problem. We already got the integral of e to the negative st cosine 80 dt, right? On problem number 4. So again, let's consider first the indefinite integral. Let's disregard the limit for a moment, the lower and upper limit. So let's try to evaluate first the indefinite integral e to the negative st cosine 80 dt. So if we go back on the previous problem, the integral of e to the negative st cosine 80 is equal to what? So we already have solved that problem, right? This one. It's equal, okay, to this integral. So let's just copy, okay? Because it will be just the same explanation, right? Integration by parts. Okay, next. So, we still have the integral of e to the negative st sine 80 dt, which we already obtained on the previous problem also. We know that the integral of e to the negative st sine 80 dt is this one. Is it this one? This one. Okay. This one. So, let's just copy. So, it will be just the same explanation using integration by parts, right? So, this is the integral of e to the negative st sine 80 dt. Okay? So, therefore, we can substitute the value of this integral of e to the negative st sine 80 dt in terms of these two expressions or two terms here. So, therefore, we will have the integral of e to the negative st cosine 80 dt equal to negative 1 over s e to the negative st cosine 80, then minus a over s, and replacing this integral of e to the negative s sine 80 dt with this one. Okay, so let's copy. Okay, quantity times negative a over s. So we can distribute again this negative a over s, multiply. So we will have negative 1 over s, copy the first term, e to the negative st cosine 80. Then multiply negative a over s times negative 1 over s. That will be positive. Okay, positive a over s squared. E to the negative st sine 80. Also multiply negative a over s times a over s. So that's negative a squared, a times a squared, over s times s squared. Integral of e to the negative st cosine 80 dt. So we should equate this to the left side, which is the original integral that we're trying to get, e to the negative st cosine 80 cosine 80 dt, right? Okay. So notice that we have the same integral on the left side and on the right side. They are both integral of e to the negative st cosine 80 dt. So likewise on the previous problem, we can combine them by transposing this negative a squared over s squared integral of e to the negative st cosine 80 dt to the left side. So doing that, we will have integral of e to the negative st cosine 80 dt. If we transpose negative a squared over s squared to the left side, it will become positive a squared over s squared integral of e to the negative st cosine 80 dt equal to the remaining terms on the right side, which are these two terms. Okay, so let's just copy. So again, we combine these two integrals. So the coefficient of this integral is 1. So we need to add 1 plus a squared over s squared. Then quantity times the original integral e to the negative st cosine 80 dt. Okay, equal to, again, this expression. But we can factor out the common terms. So let's factor out negative e to the negative st again, then over s squared. Okay. So if you factor out negative e to the negative st over s squared in the first term, what will be left is cosine 80, but we still need to have s because we factor out over s squared. We just have over s here. So we need to have s so that s over s squared will be 1 over s. Okay. How about for the second term? When we factor out negative e to the negative st over s squared, so what is left? So we factor out the negative. This one is positive. It should be minus. Okay. So we are left with a sine 80 only. So minus a sine 80. Okay. So if we combine 1 plus a squared over s squared, so that's s squared plus a squared over s squared, right? Then times the integral of e to the negative st cosine 80 dt equal, okay, let's just copy this expression on the right side. Okay. But we don't want this whole expression, right? What do we want to solve? Only this integral of e to the negative st cosine 80 dt. So we eliminate its coefficient, s squared plus a squared over s squared. How? By multiplying both sides by the reciprocal of s squared plus a squared over s squared. So its reciprocal is s squared over s squared plus a squared, right? So if you multiply this by s squared over s squared plus a squared, You can cancel out the s squared. You can cancel out the s squared plus a squared. So we are left with the integral of e to the negative st cosine 80 dt, which is what we have, which is what we want to find in the first place, right? Equal to, okay, multiply also the right side by s squared over s squared plus a squared. So you can cancel this s squared. So we just have negative e to the negative st over s squared plus a squared. Then times s of cosine 80 minus a sine 80. So this is the value of the indefinite integral without the limit, right? But the original problem is a definite integral with lower and upper limit of 0 and positive infinity. So therefore, we must also evaluate this indefinite integral from 0 to positive infinity. So substitute first the upper limit infinity to every t here. So negative of e to the negative st replaced with positive infinity over s squared plus a squared times s cosine 80 replace also with positive infinity minus a sine 80, again replace t with positive infinity. Then minus this expression evaluated this time with lower limit 0. So substitute 0 to every t here. We will have minus quantity negative e to the negative st replaced with 0 over s squared plus a squared times s cosine 80, replace it with 0, minus a sine a t, again replace with 0. So again, the problematic part or the complicated part is the analysis of this first term because it involves infinity. But it's just the same on the previous problem since we have e to the negative s times infinity. If we just restrict s to be greater than 0, it will approach 0. The power of e will approach 0, right? So therefore, the first term is just 0. Then simplifying the second term, we have negative of negative. It will become positive. E to the negative s times 0 is 0, but e to the 0 is 1. So therefore, the numerator will just be equal to 1 over s square plus a square. Then times s cosine a times 0 or cosine 0 is, again, that's just equal to 1, right? So therefore, we just have s times 1 minus a sine of a times 0, it's just sine 0, but sine 0 is 0. So we just have a times 0. Okay? So it's just equal to s. It's equal to 0. So simplifying, we just have 1 over, no, we will multiply the numerator with s. We will have s over s square plus a square. So this is the final answer. The Laplace transform of cosine 80 is s over s squared plus a squared, provided again that s is greater than 0. So another standard formula. So the Laplace transform of cosine 80 is s over s squared plus a squared. Okay. Next, number 6. Okay. What if f of t is equal to sinh 80? So sinh is hyperbolic sine 80. Okay. A again here is any real number constant. So applying the definition to find the Laplace transform of sinh 80, hyperbolic sine 80, it's equal to the integral of e to the negative st times f of t, which is sinh at dt from 0 to infinity. So to evaluate this integral, we can apply the definition of hyperbolic sine 80 using Euler's number. So remember that sinh 80 is equal to e to the 80 minus e to the negative 80 over 2. So if we substitute this value of sinh 80 in terms of Euler number in our integral, we will have integral of e to the negative st times this sinh 80, which is e to the 80 minus e to the negative 80 over 2 dt from 0 to infinity. Okay. So we can just put this 1/2 constant in front of the integral. We will have 1/2 integral of, so you can distribute this e to the negative st multiply to each term here. E to the negative st times e to the 80 minus e to the negative st times e to the negative 80 dt from 0 to infinity. So, applying the law of exponent, multiplication law of exponent, because we're multiplying same base e, so we can copy the same base e and add their exponents. So, e to the negative st plus 80, then minus, okay, same, multiplication law of exponent, copy the same base e and add the exponent e to the negative st minus 80 times quantity dt. So we can factor out t here. So 1/2 integral of e to the, when you factor out negative t here, it's equal to negative quantity s minus 80. Just like on the previous problem, right? How about this one? Minus e to the, factor out the negative t again. It will be negative quantity s plus a t. Okay? dt from 0 to infinity. So since we have two terms on the integral, we can distribute the integral symbol together with the dt. So we will have 1/2 integral of e to the negative quantity s minus 80 dt from 0 to infinity, then minus 1/2 integral of e to the negative s plus 80 dt from 0 to infinity. So how do we evaluate the first integral? So it's just an exponential function. So the shortcut formula that we apply on the previous problem. So its integral is just 1/2 then times 1 over that coefficient negative quantity s minus a times the original function e to the negative quantity s minus 80. Then let's evaluate from 0 to infinity. How about this one? So negative 1/2 integral of this one. So same formula, it's 1 over. This time, the coefficient is negative quantity s plus a. Then times the same function e to the negative quantity s plus 80. Evaluated also from 0 to infinity. Okay. So let's evaluate the definite integral for the first term. We will have, so 1/2 times this constant, 1 over negative s minus a. This will be negative 1 over 2 times quantity s minus a. Then e raised to negative s minus a. So you substitute t with the upper limit infinity. Then minus this term evaluated at the lower limit 0. So since you have negative here, negative 1 over 2 times s minus a, and you have another negative, this turns out to be positive now. Positive 1 over 2 s minus a, then e to the negative s minus a. This time substitute t with the lower limit 0. Okay, how about for the second term? So evaluate first this with the upper limit infinity, substitute t with the positive infinity. But simplifying this, we have negative 1 half times negative 1 over s plus a. That will be positive, right? Positive 1 over 2 times quantity s plus a e to the negative s plus a times t. Replace t with positive infinity. And then minus this expression evaluated at the lower limit 0. So we will have minus 1 over 2 times s plus a e to the negative quantity s plus a t replaced with 0. Okay, so what are the problematic or complicated term here? Those that involve infinity. This one and this one. Okay? So if we assign restrictions on s for the first term, if we set s to be greater than a, this power of e will approach 0, right? Also, for this one, if we assign s to be greater than negative a this time, because this term is different from this term. The exponent of e here is e to the negative s minus a, while here it's e to the negative s plus a. That's why they have different restrictions for s, for this term to converge to 0. For the first one, s should be greater than a, but for the second one, s should be greater than negative a. So therefore, since we have two restrictions for s, we should get the intersection. Okay? So how do we analyze this to get the intersection of these two restrictions? So notice that s greater than 0 can also be written as a less than s, right? How about this one? If we multiply this both sides by negative, so negative times s, that's negative s. But since we multiply both sides of the inequality by a negative number, negative 1, we should flip the inequality symbol to its opposite. It will become less than now. So that negative times negative a is positive a. Okay? So, how do we combine this? So, this is the same if negative s is less than a and a is less than s. If we combine this inequality, this can be negative s less than a less than s, right? Or if you want to use the absolute value notation, negative s less than a less than s is the same as absolute value of a less than s, or s greater than absolute value of a. So any of these will do for the restriction of s. So if we assign, let's say this one, so if absolute value of a is less than s, therefore, these two terms both will converge to 0. Those terms with infinity, this one and this one, right? So therefore, sige, copying this whole expressions here, if we assign these restrictions on s, so this term will now be 0, right? How about this one? Plus 1 over 2 times s minus a. So e to the negative s minus a times 0, it's just 0. E to the 0 is 1. So we just have positive 1 over s over 2 times s minus a times 1, or just 1 over 2 times s minus 1. Okay, plus, okay, this one, since we already have restriction for s, it will now converge to 0. For this one, it's negative 1 over 2 times s plus a. Then e raised to negative quantity s plus a times 0 or 0. E to the 0 again is just equal to 1. So therefore, we have times 1 here, or simply this expression, negative 1 over negative 1 over 2 times s plus 1. So it's just equal to 1 over 2 times s minus a minus 1 over 2 times s plus a. Okay? We can combine this as a single fraction. So what is the LCD of 2 times quantity s minus a and 2 times quantity s plus a? It's 2 times s minus a times s plus a, right? So divide this LCD first by the denominator of the first fraction, 2 times s minus a. You can cancel out this 2 times s minus a. You are left with s plus a. Then multiply this s plus a times the numerator 1, s plus a. Okay, so you have s plus a, then minus, okay, also do the same here for the second fraction. Divide this LCD by the denominator, 2 times s plus a. Okay, what can you cancel? You can cancel 2 and s plus a, right? You are left with s minus a times the numerator 1, still s minus a. So you will have quantity s minus a. You simplify, so you distribute this negative sign, s plus a minus s, negative of negative a, positive a, over 2 times s minus a times s plus a. So you can cancel out this s minus s is 0, but you can combine a plus a, 2a, over 2. So if you multiply s minus a times s plus a, so this is just a special product. It turns out to be the difference of two squares, right? So it's equal to s square minus a square. You can still cancel out these two. Therefore, the final answer is a over s square minus a square. So this is the Laplace transform of sinh at, provided that the absolute value of a is less than s. So memorize this, another standard Laplace transform formula. Okay, Laplace transform of hyperbolic sine of 80 is equal to a over s squared minus a squared. Okay? Okay, next. 6, so 7. What if hyperbolic cosine 80? So again, a here is any constant real number. So applying the definition for the Laplace transform of f of t, so Laplace transform of cos 80 is integral of e to the negative st times f of t, which is cos 80 dt from 0 to infinity. Again, just like on the sinh 80, we also have definition of cos 80 in terms of the Euler's number. This time, cos 80 is equal to e to the 80 plus e to the negative 80 over 2. So substitute this value of cos 80 in terms of Euler's number in our integral. We'll have integral of e to the negative st times cos 80, which is this expression, e to the 80 plus e to the negative 80 over 2 dt from 0 to infinity. Again, this constant of 1/2 is, it's just a constant. You can just put it in front of the integral first. So we will have 1/2 times the integral of, so we will distribute also this e to the negative st to every term. So e to the negative st times e to the 80, then plus e to the negative st times e to the negative 80 quantity times dt from 0 to infinity. So applying the multiplication law of exponent, So copy the same base e and add the exponents e to the negative st plus 80. Also here, copy the base e and add the exponent negative st minus 80. Quantity times dt from 0 to infinity. So you have 1/2 integral of e. You factor out negative t here. It will be negative quantity s minus 80 plus also factor out negative t here. It will be negative quantity s plus 80. Just like on the previous problem. Quantity times dt from 0 to infinity. So since we have two terms on the integral, we can distribute this integral symbol together with the dt. So you have 1/2 integral of e to the negative quantity s minus 80 dt from 0 to infinity, then plus 1/2 integral of e to the negative quantity s plus a t dt from 0 to infinity. So to evaluate this integral, it's just the same on the previous problem for the sinh, right? So it's 1/2 times integral of this is 1 over negative s minus a times e to the negative quantity s minus 80, then evaluate from 0 to infinity. Plus, for this one, we have 1/2 integral of e to the negative quantity s plus 80. So it's 1 over negative s plus 80, then e to the negative quantity s plus 80, evaluated from 0 to infinity. So let's evaluate the lower and upper limit for both of these two terms. So for the first term, substitute infinity to every t first. So 1/2 times 1 over negative quantity s minus a, it's just the same as negative 1 over 2 times quantity s minus a, e to the negative s minus a, t, replace it with the upper limit infinity, then minus this expression evaluated at 0. Since we have negative 1 over 2 times s minus a, and we have another negative here, this will become positive already. 1 over 2 times s minus a, then e to the negative s minus a t, which is replaced with the lower limit 0. So for the second term, evaluate upper and lower limit. So 1/2 times 1 over negative s plus a is equal to negative 1 over 2 times s plus a, right? E to the negative s plus a t, replace with the upper limit infinity. Then minus this expression evaluated at 0. But since this is negative and we have another negative, this will become positive. Okay, positive 1 over 2 times s plus a, e to the negative quantity s plus a t, which is now replaced with the lower limit 0. So, for the terms with infinity, this one and this one, we just need to apply the same restrictions on the previous problem for the Laplace transform of sinh, right? So, absolute value of a should be less than s. These two terms will converge to 0, right? So, therefore, 0 plus 1 over 2 times s minus a e raised to 0, right? But it's just equal to 1. E to the 0 is 1, so it's just equal to 1 over 2 times s minus a. For the second one, we have minus 0, right? Because we already have applied restrictions for s. It will now converge to 0. For this one, plus 1 over 2 times s plus a, e raised to 0 again. But e raised to 0 is 1. So therefore, it's just equal to 1 over 2 times quantity s plus a. So what we have is just 1 over 2 times s minus a plus 1 over 2 times s plus a. We can combine this as a single fraction. What's the LCD of 2 times s minus a and 2 times s plus a? So it's 2 times s minus a times s plus a. So combining as a single fraction with the LCD, 2 times s minus a times s plus a. So divide the LCD first by the denominator of the first fraction. You will cancel 2 and s minus a. You are left with s plus a times the numerator 1, s plus a, right? So s plus a, then plus, so doing the same on the second fraction. Divide the LCD by the denominator, 2 times s plus a. So you will cancel 2 times s plus a. You are left with s minus a. Then times the numerator 1, s minus a. Combining similar terms on the numerator, you can cancel out a because a minus a is 0. Then s plus s, 2s. Over 2 times, so you can multiply again s minus a times s plus a. Difference of two squares, right? S square minus a square. You can cancel out the 2. The final answer is s over s square minus a square. So this is the Laplace transform. Laplace transform of cos 80 provided that absolute value of a is less than s. So another standard integral formula. I mean Laplace transform formula. Okay. Okay, next 7 8. Okay. Next we consider what I've said on the earlier on this video, because we have the generalized version of the Laplace transform of t to the n, which is equal to n factorial over s raised to n plus 1, where n here is just a whole number, so it can be equal to 0, 1, 2, and so on. What if we want to find the Laplace transform of f of t, let's say t to the alpha, where alpha is greater than negative 1. Okay, meaning it doesn't necessarily have to be whole numbers only. And any real number as long as it's negative. Alpha is greater than negative 1. It can be 1/2, 1/4, and so on. So we will still apply the formula for finding Laplace transform. So Laplace transform of t raised to alpha is equal to the integral of e to the negative st t raised to alpha dt from 0 to infinity. Okay? But we won't apply integration by parts here. It's different case now because the power of t is restricted, less restricted compared to here, because here should be only exponent of t, which is n, should only be whole numbers, but this one is any real number greater than negative 1. We will apply substitution. Okay. If we let u be equal to st, or if we solve for t here, divide both sides by s, t is equal to u over s, right? If we get the derivative of both sides, derivative of u, it's du. Derivative of st is s dt. S is just a constant here. T is the independent variable. Okay. Therefore, if you want to solve for dt, divide both sides by s. dt is du over s. Okay. So, since we're using u substitution, we also should get the new lower and upper limit in terms of u. So, if the original lower limit value in variable t is 0, so if t is 0, we substitute this value of t0 in the substitution u is equal to st. We will have u is equal to s times t, which is 0. U is also 0. So this is the new lower limit of the integral in the new variable u. What if t is infinity for the upper limit? So t approaches infinity. Substitute in the u is equal to st. U is equal, or since t is approaching infinity, you should also approach infinity if s is greater than 0, right? Therefore, u is also approaching infinity. So basically, we just have the same lower and upper limit when we use this substitution. Okay, so substituting in the original integral, this will be, okay, integral of, so e to the negative st is u, right? And t is, what is t? U over s. U over s raised to alpha. So quantity raised to alpha. And then this dt is equal to du over s. Then we have the same lower and upper limit in terms of u. It's still 0 to infinity. So this is now the new integral in terms of u. Let's simplify. So distribute the exponent alpha on u and s. So it's integral of e to the negative u to the alpha over s to the alpha times du over s from 0 to infinity. So the independent variable in this integral is now u, right? So therefore, alpha and s are considered constant. So if you multiply s alpha times s to the first under the denominator, it is the same as integral of e to the negative u to the alpha du. So over s raised to alpha plus 1. Because they have the same base s, you just copy the base s and add the exponent alpha plus 1. Which is a constant, so you can just put in front of the integral this 1 over s raised to alpha plus 1. So 1 over s raised to alpha plus 1 times integral of e to the negative u to the alpha du. So this is from 0 to infinity. Okay. So far, this is the expression for the Laplace transform of t to the alpha, provided that alpha is greater than or equal to negative 1. So to have uh, a better formula, instead of having integral here, for the Laplace transform of t to the alpha, let's apply the gamma function. So if you're not aware, we have the so-called gamma function. Gamma function, let's denote by this symbol. Okay. Gamma function of, let's say, alpha. The definition of gamma function of alpha is another improper integral. Integral of integral of t to the alpha minus 1 e to the negative t dt from 0 to infinity. So this is another improper integral, right? Because there is an upper limit of infinity. Where t here is a dummy variable, meaning you can assign other variable than t. You can assign u, you can assign w, etc. Okay? So, if you try to relate this integral to this definition of the gamma function, okay, how can we relate this integral to this integral? Notice that they have both e to the negative t, power of e. Remember that t here is a dummy variable. Likewise here, u is a dummy variable. Okay? They just differ from this power or from this base, the power of t here is alpha minus 1, while the power of u here is alpha. You can adjust in the gamma function here. If you try to find the gamma of alpha plus 1, therefore it is equal to t raised to alpha minus 1, but alpha now here is alpha plus 1. So you should replace this alpha with alpha plus 1, then minus 1, then e to the negative t as is dt from 0 to infinity. Therefore, it's now equal to integral of t, so cancel out the negative 1, t to the alpha e to the negative t dt from 0 to infinity. Okay? So, if we compare this obtained formula so far for Laplace transform of t to the alpha, they are now the same, right? Because t and dt, just like what I've said, t and u here are dummy variables. You can or you can have any variable that you want. So, therefore, I can also substitute, let's say, u here in the formula. So, gamma of alpha plus 1 is also the same as the integral of t to the, let's use now u to the alpha e to the negative alpha du from 0 to infinity. Which is, if you compare, therefore, these expressions are the same, equivalent both to gamma of alpha plus 1. Therefore, the final formula for the Laplace transform of t to the alpha is 1 over s raised to alpha plus 1 times this integral equivalent to gamma of alpha plus 1. Okay, provided that alpha is greater than negative 1, also s is greater than 0. Or simply gamma of alpha plus 1 over s raised to alpha plus 1. So this is the Laplace transform of t to the alpha, which is another standard formula. So this is the generalized version of the Laplace transform of t to the n. Okay? This one. For this one, you just have whole numbers value of n, but for this one, you can have values of exponent for t alpha greater than negative 1. All real numbers greater than negative 1. Okay? So, you should memorize this formula, another standard Laplace transform formula. But here, you should apply some properties of gamma function. So, some properties of gamma function. So, this is just derived from the original definition of gamma function. So, the gamma function of alpha is equal to alpha minus 1 factorial. Okay? And then, the gamma of alpha plus 1 is equal to alpha gamma of alpha. But from this one, okay, you can also conclude that if you substitute gamma of alpha plus 1 here, it will be alpha plus 1 minus 1 factorial. So therefore, gamma of alpha plus 1 is just alpha factorial, right? So this is also equal to alpha factorial. Also, gamma of 1/2 is always equal to the square root of pi. So this next formula is useful. The gamma of m plus 1/2 is equal to 1 times 3 times 5 dot 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 until 2m minus 1 over 2 to the m times the square root of pi, where m is integers 1, 2, 3, and so on. Also, the gamma of negative m plus 1 half is equal to negative 1 to the m times 2 to the m square root of pi over, so 1 times 3 times 5 times dot 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 until 2m minus 1, where m is also integers such as 1, 2, 3, and so on. Okay, so this will be useful later when we're trying to find the Laplace transform of power of t raised to, let's say, fractional power. Okay, we can apply this formula. So you just memorize these properties of the gamma function. Okay. So I think these are the standard Laplace transform, the basic standard Laplace transform formula that you must memorize. So the first one, the last one, okay, and then the first few. Okay, let's just recall. Okay, so recalling all the standard Laplace transform formula. Okay, that we have derived in this video. The first one, Laplace transform of 1 is 1 over s. Laplace transform of t to the n is n factorial over s raised to n plus 1, where n is 0, 1, 2, and so on, whole numbers. 3. Laplace transform of e to the at is 1 over s minus a. A is any constant. 4. Laplace transform of cosine at is s over s minus a squared. 5. Laplace, this should be plus, sorry, s squared plus a squared. Laplace transform of sine at is a over s squared plus a squared. 6. Laplace transform of cos at is s over s squared minus a squared. 7. Laplace transform of sinh at is a over s squared minus a squared. And 8. Laplace transform of t to the alpha is gamma of alpha plus 1 over s raised to alpha plus 1, provided that alpha is greater than negative 1. So on the future videos for this series of live stream for Laplace transform, we will use all this standard formula. So we won't be deriving, or we won't be finding Laplace transform of certain function of t using the integral definition anymore. But we will just use this derived formula to find the Laplace transform of any function of t. Okay, so you just memorize this formula. Okay, so I think that's it for this video. So I hope you learned something from this video. See you on my next live. I will just put the link of Laplace transform. I mean the playlist for advanced engineering mathematics. If you want to watch my old videos there, you can just check the description. And we will just continue this topic all about Laplace transform on the next live. So make sure you subscribe to our YouTube channel and click the notification bell so that you will be updated whenever we have new uploaded videos and upcoming live stream in the future. So stay tuned for that, for more live streams all about Laplace transform. Okay? So good luck and God bless to your studies, everyone. See you on my next live. Bye-bye.